Hi everybody. I'm gonna give you a little recap about what you've learned in quantum so far. So for example, if you were looking to find the probability, you would take, remember, the square modulus of the normalization times some sort of integral over all the space of the square modulus of the wave function. So how do we actually find n? So the probability over all space should be equal to what? Yeah, exactly. You probably said it in your head. It's equal to 1. All right. So then you have 1 is equal to some sort of integral over all space. So essentially, we're going to use that process to find n. So additionally, and be careful, because this whole entire thing is what's equal to 1. This itself is not equal to 1. This is just the probability density function, not the probability. So we also know that we can find the expectation of, let's say, x. So we know that that's going to be just that integral again. Oop, the pen went away. Again, n squared, integral of, now that's the square modulus, and what we have to do essentially when we're taking the expectation is we sandwich that right in the middle. So we have the complex conjugate of psi, and then x in the middle, and then psi here, dx. Right, and in this case, since psi is just a function of x, it commutes with x, so you could just rewrite it and move the x around wherever you wanted. Now, in general, that should be an operator. The expectation of an operator A is equal to that n squared psi A psi dx. Now note sometimes n is already in the wave function. And what I mean by that is psi is equal to n times something, right? So there's two more things I want to say. The expectation of momentum, for example, using this same exact formula, we'll even write it without the n this time, is equal to psi star of x. And what is the momentum operator in terms of x? Just think about that for a second. All right, it's been a second. Minus IH bar d dx of psi of x dx. Okay, and I want to talk about one more thing, the variance. So we can also calculate the variance using this sort of integral. So, for example, if we wanted to calculate, let's say, sigma x squared. This is equal to psi star of x. And what goes in here? Yeah, it's going to be, you were probably thinking that, x minus the expectation of x squared psi of x dx, which you sort of saw in your first homework assignment that that's true. So for example, if we wanted to do the variance sigma p squared, it would be psi of x and then we'd have P minus, that's a hat, minus the expectation of P, psi of x dx. Because the operator x is just equal to x, you just multiply something by x. So here's what we have to work with. So let's see an example now. Alright, so let's consider the example then that psi of x is equal to n e to the minus alpha x squared. So some sort of Gaussian times the normalization constant. So one thing that I want to specify is this alpha can live anywhere. So just in case you aren't familiar with this, this is an element of. And that C is the complex numbers. Alright, so if we wanted to find the normalization for this, we would remember we have that integral that we set equal to 1. And so we have n squared times the integral all over space, which is minus infinity to infinity this time, of the square modulus of the wave function. But there's no imaginary part except for maybe that alpha, right? So if we have the possibility that alpha is complex, then we would have something that looks like the following. Oopsies. It would be e to the minus alpha complex conjugate of alpha x squared, e to the minus alpha x squared dx. Now if we combine this, this looks like n squared, integral from minus infinity to infinity of e to the minus alpha conjugate plus alpha x squared dx. Okay, and what I want to highlight about this part is very, very small little proof of this sort of thing. So if you have, I'll do this in red. So if you have, let's say, z is equal to a plus ib, then z star is equal to a minus ib. So if we add these two together, we see that we get 2a, or 2 times the real component of z. So in our case with alpha, we would get 2 times the real component of alpha. So let me write that out. So using this, our alpha conjugate plus alpha is equal to 2 re alpha, which I'm just going to call a constant beta. So we can just sort of toss that aside for now. Okay, so using this knowledge, we have that this is equal to n squared, the integral from minus infinity to infinity of e to the minus beta x squared dx, which is a Gaussian integral that you learned in the first video. So just maybe pause for a second in your head and think about what the result should be. And okay, you probably paused and thought about it, so that's great. So this integral would give you the square root of pi divided by beta, right? Okay, cool. So just take a second to yourself and think about what that's equal to. And if you said that that was equal to 1, you were absolutely correct, because that's the probability over all space. So now we can solve for n. So we get that n is equal to beta over pi to the 1/4. Or if you want to put in the previous example, or not example, but the result, 2 times the real component of alpha over pi to the 1/4. And if alpha was real, that r means in the real numbers, we would have that n is simply equal to 2 alpha divided by pi to the 1/4. So that's how we found the normalization constant for that one. Hopefully that made sense. So if we wanted to find the expectation, for example, let's just set that up. And let's also just set up the expectation for, let's go with momentum. And then we'll call it good, because I think this has been a lot of information for you to handle. Hopefully it made sense. So the expectation of x is going to be the integral of over all space minus infinity to infinity of psi star x psi x dx. But we know that normalization constant. So this is just going to be 2 alpha divided by pi to the 1/2, because it's 2 normalization constants. Then the integral from minus infinity to infinity of x. Let's just assume we're going to use that result that alpha is real now. So we have e to the, looking back at our original wave function, so it'd be e to the minus 2 alpha x squared. So we have 2 of those now. dx. So that is great. And you can evaluate that using a simple u substitution. Alternatively, you could use the symmetry of the integral. So you have that the pen's not working. So you could use that this is a symmetric function, and this is an anti-symmetric function, to simply say that this has to be 0. Because when you have a symmetric function times an anti-symmetric function, you get an anti-symmetric function back. And finally, if you want to calculate the expectation of momentum, this is equal to the integral from minus infinity to infinity of psi star x times that minus IH bar d dx. We want to operate that on psi of x dx. So this is going to be equal to minus IH bar times that normalization constant squared, and the integral from minus infinity to infinity, oopsies, that's a terrible infinity, and then we have e to the minus alpha x squared here, and if we take the derivative of that, you should notice that the derivative gives us, okay, so yeah, you probably got the derivative right in your head. So if we take the derivative of that function, you're going to get a minus 2ax here, and then e to the minus alpha x squared dx. Oops, sorry, that's an alpha, not an a. So let's take a look at this one last time. So just by inspection, we can actually take a look here, and we can combine these to, so we get e to the minus 2 alpha x squared. And here we have that x again that's popping up. So here we have our anti-symmetric part, and with the stars, we have the symmetric part. So therefore, I'll even write it in green, therefore we have that the expectation of momentum is equal to 0, which is an expected result, right? So I hope you learned a lot with this quantum recap, and as always, please let me know if you have any questions, and have a great day. Don't forget to be awesome. Thanks for watching.